Computing 2, An Introduction to Programming, Part 2. During this section we're going to work through those examples that I gave you and then look at some actual queries that we could apply to the second data set. My first example then was a table containing accession codes, names and species. Now you should have spotted from this that the species information is being repeated, so we want to move that out into a separate table. So what we would do is have one table containing the accession code, the name and the species identifier as a numeric item instead of as the text, and then we have a second table with the species identifier and the species name. Our second example was a bit more complicated, and as I said, this needed to be divided into 4 separate tables. So when you look at the information here, you see clearly that these last 2 columns need to go into separate tables because they contain repeating data. So what are the other 2 columns? Well, one will be the proteins and one will be the mutations, because you can think of those as separate entities. So from this we can create what's known as an entity relationship diagram. So here are our 4 entities: species, proteins, mutations and effects. Now this means that one species can link to n different proteins. So it's a one-to-many relationship. One species can be found in many proteins. And similarly, we have a 1-to-n relationship between proteins and mutations. So one protein can have many mutations. And finally, one mutation will have one effect. So how do we create these tables? Well, the protein table would look like this. The protein has an accession, a name, and a species identifier. The species table links the species identifier to the species name. The mutation table has the accession code of the protein. So if we go back to the proteins table, we're going to use this because this is a unique piece of information. We're going to use this as an identifier to identify a particular row in this table. So the mutations table has an accession code for a protein. It has the native amino acid, the residue number that's mutated, and the mutant amino acid. And then it has a link to the effects table to say what the effect of this mutation is. And the effects table looks like this. So an effect identifier and a disease status, a piece of text. Okay, let's look at some example queries then using that second set of tables that would allow us to, first of all, recreate the full table, then find all the mutations that occur in mice, and find which species have mutations from a leucine to something else. Before we look at the SQL to implement those examples, I'm going to look at the idea of an entity relationship diagram in a bit more detail. Now, this is very simple. All it is the 4 tables that we have: species, proteins, mutations and effects. And within each of these boxes we then put the names of the columns in the table. What we also provide though is the links between the tables using this crowfoot notation. So this is simply showing you that it's a one-to-many relationship, and I've put in the letter N as well to show that Here we have a one-to-one relationship. So one mutation has one effect, whereas one species can be seen in many proteins, and one protein can have many mutations. The other thing that we're introducing here is the concept of a primary key. Now, primary keys here are indicated with a star, and this indicates that if you know that piece of information, then you will find a unique record in that table. So this is the concept. The primary key is unique. In the case of the mutations table, we don't have a simple primary key. Instead, we have what's known as a composite primary key. So you have to have a particular protein accession, a particular residue number, and a particular mutant residue at that site in order to identify a particular individual row in that table. The other thing that we have is foreign keys. So a foreign key in a table, like effect ID here, is a primary key in another table. And this is what we use to link the tables together. So this one's foreign key links to this primary key, so we know that for a particular mutation we will have this effect. In this case, the accession code is both part of a composite primary key in the mutations table, and it's a foreign key of the proteins table. So again, this concept of foreign keys is what allows us to link something in one table with a particular row in another table. This query would allow us to recreate the full table. We've seen a couple of little examples of SQL queries in the first lecture, and just to summarize here, then the select is what you want to come out of the database. From is the tables that we're querying, and we can optionally, as we have done here, create abbreviations for the table names. The where is the things that we want to be true, and in this particular example we're just using these to join the tables together. So let's look at these. We've specified in the from that we're interested in the 4 different tables: species, proteins, mutations and effects, and we're going to abbreviate those to S, P, M and E. So what we want to pull out is the accession code from the proteins table, the native residue from the mutations table, the residue number from the mutations table, and the mutant residue from the mutations table. We want the protein name, we want the species from the species table, and we want the disease status from the effects table. And in these 3 statements we're joining the tables together, so we're making sure that the mutation effect ID is the same as the effects effect ID. We're making sure that the mutation accession is the same as the protein accession, and we're making sure that the protein species ID is the same as the species ID. In this second example, we're looking to find all the data but just for mice rather than all species. So in this case we have exactly the same query that we had last time, but we add an extra AND clause to the where statement. So we're specifying that the species name must be equal to mus musculus. Since we know that the species identifier for mouse is the number 2, then we could also put this query as s.speciesId equals 2. Our third example was to find what species have mutations from a leucine. In this case then we're only interested in pulling out the species name. So we do select s.species, So S is an abbreviation for the species table. We're also not interested in the effects of mutations here, so we don't need that information, and therefore we don't need the effects table. The parts of the where statement are fairly similar to what we had before. We need to join these three tables together. So we're going to say that the accession in the mutations table must match the accession in the proteins table, and the species ID in the proteins table must match the species ID in the species table. And finally, we put in our requirement that the native residue is a leucine. So we say mutations.native equals L. When we run this query, we don't care about the effects table, and the select statement has said that we are only going to print the species. So what we find as output from this is that we get species, Homo sapiens, Homo sapiens. And these would have come from the 4th and 5th entries in the full table. However, it would be nicer if we only had the output once. We don't really want to see lots of occurrences of Homo sapiens. And what we can do to have that effect is exactly what we did before, but put in this extra keyword distinct. Select distinct species, so that will only output each species once, and the output is exactly what we want. We're going to take another short break at this point, and the third section of the lecture will go on to look at algorithms and programming using the language Perl.